Okay, Bolzano-Weierstrass, one of the most important results of this course. Who can tell me about it? Anybody? Who can tell me about it? What is it? What are we talking about here? Well, we're talking about accumulation points, of course, right? Right. So accumulation points. Right. So right. Right. And so, what does the Bolzano-Weierstrass theorem say? Just to give a quick review. Yeah, Mia.
If S is an infinite set and bounded, then S has at least one accumulation point.
Right. So S is a subset of R. If it's an infinite and bounded set, then it has at least one accumulation point. Okay. And what was the idea of the argument? Can anyone talk about the idea of the argument? Try to be able to talk about things. It's useful. If you can only read and write mathematics, then it's hard to converse with other people. Unless you only write them letters. I should say that when I was in college, I always worked by myself, and I basically only read and wrote mathematics. And then there were other people who always worked in groups, and they were talking with each other all the time about mathematics. And I never really developed the knack of talking to other people in English or in mathematics. But I find that the people who can talk with others, they get information a lot more quickly. So try to be able to say what things are, just give some sort of rough idea of what's going on. Mia, great.
So you split the set in half, and then one of those is infinite, and then you just keep doing that. That's
right. So you have your set, it's bounded, right? So your set lies between two bounds, right? Lies within some interval AD, right? So that's you call that interval I0 or I1, okay? And then what you do is let's call it A1, B1, okay? And then you divide it in two. You say, okay, I've got infinitely many points in here, so I'll divide it in two. I know that one of these intervals has to have infinitely many points, one or both, but at least one has to have infinitely many points. So call that, maybe it's the one on the left, call that one I2, right? And then divide I2 into two parts and keep on going, right? Choose the one that has infinitely many. Choose the one that has infinitely many. That's I3, maybe I4, the one on the left, maybe the one on the right has infinitely many, and so on and so forth. And you get this decreasing sequence. You get a sequence of nested intervals. So obtain a sequence of nested intervals, I sub n, right? Where I sub n, intercept S has infinitely many points, right? For each n, right? So the number of points in the intersection is infinite for every n. Okay, right? And further, it's possible to see. And then how do you find the accumulation point? What's the idea? How do you find the accumulation point? You've got all these intervals. What do, Raleigh?
You continue splitting in half.
Yes.
And since the expression would be 1/2 n minus 1 of the initial interval, as n goes to infinity, that is, you do that infinitely many times, that will just converge to a single point.
Okay, so so the length, notice that the length of n goes to 0, right, as n goes to infinity. So notice that the length of n, and this is the length, the length of I sub n goes to 0, right? And so, one of your homework problems is that, so homework problem is that the intersection of the isobens is non-zero, is not empty, right? So there's somebody in there, right? And since the lengths of the intervals goes down to 0, this tells you that there's only one point. There exists only one point in the intersection. Okay. So the homework problem is to show that there exists a point there, and the fact that the lengths of the intervals goes down to 0 implies that there's only one point in there. So there's one and only one point. Some people, you may be amused to hear like this as one, like just like if and only if, right? There's one and only one point. Okay, right? And then you show that, so this is to say there exists a point in the intersection, and this says that there exists only one point in the intersection, right? And that point is what we're going to claim is the accumulation point. Right? That point is the accumulation point. Okay. Now that needs to be proven, right? But it's not difficult. You say, well, look, if this is my accumulation point, let's call it A. Right? If this is my accumulation point A, and I take any epsilon interval around it, so here's my epsilon neighborhood. Right? How do I know that that epsilon interval, epsilon neighborhood intersects S? Well, can anyone say it? How do I know that that epsilon interval intersects S? Katie, do you know? No?
What do you mean by intersects S?
I mean, when intersects S in a non-empty way, so that there are points of S inside here. Right? So if I have these guys don't intersect. Right? Here, this interval intersects this interval. So there's a non-empty intersection. Okay. Can anyone say, yeah, Mia?
Do you choose the interval that is less than the length of epsilon?
Yes, exactly. So you say, well, look, this A is in the intersection of all the i's, and each of the i's has infinitely many elements of S in it, right? So you say, okay, I'm going to just choose choose I sub capital N big enough such that the length of I sub n is smaller than epsilon. Right? The length of I sub n, choose n huge. Right? Choose some huge n so that I sub n is smaller than epsilon. Right? Well then, since it intersects A, we know that I sub n has to lie, let's say epsilon over 2, just to be safe. We know that I sub n, then I sub n lies inside of the, right, then I sub n lies inside epsilon, right? But then there's infinitely many, since there's infinitely many points of S inside here, there's infinitely many points of S inside the punctured neighborhood. And that's it. So it's Bolzano-Weierstrass. Okay. Well, we've left out a really hard part, or not a really hard part, but we've left out one important part, which is the homework problem, the group problem. I'll let you do that this weekend. Right, so the group, let's move the group presentations to Wednesday, because that will give me the chance to, that way you turn in the the drafts on Monday, and I'll go over them and get them back on Tuesday, and the presentations will be on Wednesday, just like last time. Okay, so any questions about Bolzano-Weierstrass? Okay, let's go on. So again, continuing in chapter 10, Cauchy sequences. Okay, also a really important idea. Really important idea. Okay, so Cauchy sequence. Can somebody tell me who can tell me what a Cauchy sequence is? Anybody? What's the difference between a Cauchy sequence and a convergent sequence? You have some sequence. If something happens, we call it a Cauchy sequence. Yeah, okay.
Isn't it something like if the absolute value of s of n minus x of m is less than epsilon, or
Okay. If I saw this, you'd say, well, what is epsilon? Are you saying,
epsilon greater than 0?
so given any epsilon greater than 0, given any epsilon greater, and what are m and n?
Those are values of the sequence, I guess.
Okay.
Or are they consecutive values?
So can they be any values? Are you saying that given any epsilon, it's true that any pair is within epsilon of each other?
It's easy. I'm not sure.
If that were true, so it's can anyone add the missing phrase here? Because this would be this would cause your sequence to be actually only a single point. If you said given any epsilon, any m and n are within epsilon of each other, well then any a sub n and a sub m would have to be exactly the same point, and that would mean your sequence be a single point, which is not what you want. Does anyone know the missing words we need to put in here? So there exists an n such that if n and m exceed that thing, a sub n and a sub n is epsilon. So there's some time dependent on epsilon, so that past that time, everybody's within epsilon of each other. So it's sort of a funny thing. You don't know. You notice that there's no mention of a limit here, right? There's no limit value, right? What we're rather saying is that if you take anybody in the sequence, a_n and a sub n, well then their distance is smaller than epsilon, right? Their distance is smaller than epsilon. Their distance is smaller than epsilon. Given an epsilon, you can find a time past which all pairs are within epsilon of each other. Okay. So this is basically saying that the sort of intuitive picture is that the diameter of the tail can be made as small as I want. Okay. That's how I think about Cauchy sequences. That you have your sequence. Right? A1, A2, A3, A4, A5, etc., 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 etc. And what it's saying is that if somebody gives you an epsilon, like somebody says epsilon is 1, okay, and you can say, well, past some point, everybody is within 1 of each other. Okay, past some point, past some time, here's the first guy in like past that time, past some guy, everybody's within 1 of each other. Okay, right? And somebody gives you another epsilon, you can say, okay, there's some epsilon of 1/2. Well, there's another point so that the tail, past that guy, everybody's within 1/2 of each other. Okay, so the diameter of the tail can be made as small as you desire.
What does that say before the word one? Very end?
I.
Sorry, can you explain it?
Yes, yes. So, given any epsilon, there's a time past which everybody's within epsilon of each other. Okay. If I say epsilon is 1, well, you can say, oh, past this time, all guys are within 1 of each other. No matter what pairs I take, they're all distance 1 of each other.
What do you mean by time?
If you think of a sequence as being a map 0, 1, 2, 3, 4, 5, right? 0, 1, 2, 3, 4, 5, right? 1 goes to, at time 1 we're here, at time 2 we're here, at time 3 we're here, at time 4 we're here, at time 5 we're here, etc., right? Or if you want to think of it like this, okay, so 1, 2, 3, 4, 5, 6, 7, blah, blah. Right? You've got your guys. Okay, right? Given any epsilon, you can find a time past which all heights are within epsilon of each other. Okay, so the difference between any two heights is smaller than epsilon. Okay, I've drawn my sequence in R2 here. So here my sequence is going from R to R2. That's maybe not so helpful for you because we've been thinking of sequences as going from R to R. But I hope you get the idea. Right? I'll draw it in R1 if you want. So here's A1, say, A2, A3, A4, A5, A6, A7, etc. So there's a bunch of points here, right? Given any epsilon, I can find a time past which all these guys are within epsilon of each other. Okay, so if I said, I'd like everybody to stay within this distance of each other, okay? And you'd say, oh, look, past time 5, that'll do. Look, everybody past time 5 is within this distance of each other. Okay. And I say, okay, I'd like everybody to stay within this distance of each other. And you'd say, well, maybe past time 7, everybody's within this distance.
Are you arbitrarily choosing the position of A4 or A5?
It's just an arbitrary sequence. Yeah, it's a sequence. But I'm trying to give you some sense of what a Cauchy sequence looks like. Right? A Cauchy sequence is one where you can control the size of the tail. Okay. So so this is the definition here, right? Given any epsilon, there's a time past which all pairs are within epsilon of each other. All pairs are within epsilon of each other. Well, let me just go on and see if I can. We'll make some observations. So, simple observation. If a sequence is Cauchy, then it is bound. sequence is Cauchy, then it must be bounded. Maybe, okay, let me step back for 1 second and say, here's an example. Let a sub n be 1 over n. Let a sub n be 1 over n. So at time 1, right, you get a1, so this is 1, this is 0. Right. Here's a1, I'm sorry, yeah, here's a2, here's a1, here's a2, here's a3, here's a4, and so on and so forth. Right? And then they have accumulation point at 0. Okay. Now this is a Cauchy sequence. This is a Cauchy sequence, right? Because given any epsilon, I can find a time past which everybody is within epsilon of each other. Okay. If I say I'd like everybody to be within 1 of each other, then you just say, well, take my n to be 1. Everybody's within 1 of each other. Right? If I say I'd like everybody to be within a half of each other, what do I choose as my n? 2, right? Because then everybody lives in this interval 0, 1 half, right? Everybody's in 0, 1 half, and so the tail is smaller than 1 half, right? The tail is smaller than 1 half, and so on and so forth. Okay, so here's an example of a Cauchy sequence, and I hope it's clear what we mean by that you can control the diameter of the tail. So if a sequence is Cauchy, then it's going to be bounded. Does that seem true or false? Sequence is Cauchy, then it's going to be bounded. Why would that be? If you think about the tail, yeah, Mia, go ahead.
Well, if you know that at a certain point everything past it is within epsilon, then you know that it's bounded by epsilon, and then everything before it is a finite number, and a finite set is bounded.
Yes, yes. So the intuition is pretty clear, right? A Cauchy sequence means that you can control the diameter of the tail. So just say, let the diameter be 1, right? Then you know that the tail lies within some unit interval, right? The tail is going to lie within some unit interval, and so that part is bounded. And then the part before is finite, and so you know that part is also bounded, right? So it's kind of similar to the previous argument. This is similar to the sequence converges, that it's bounded. It's almost exactly the same argument, but just you have to modify it slightly to use the Cauchiness. Okay, so I'm not gonna do it. Maybe I'll leave it as an exercise. Maybe that'll be one of the exercises for tonight. Okay. More important for us, I hope we can do it, is if A sub n is convergent, then A sub n is Cauchy. Okay. Any convergent sequence has to be a Cauchy sequence. Okay. Why is that sort of intuitively clear? Why is that intuitively clear? Convergent means, well, that you become closer and closer to some point, right? Cauchy means you can control the size of the tail, right? Convergent means you can make your points as close to L as you want, right? Cauchy means you can make your points as close to each other as you want. Right? So why does being close to L force close to each other? What do we need to say? Mia, you're on a roll.
If it's convergent, it means it's close to, it's within epsilon of L.
Yeah.
And then if it's Cauchy, it just means it's within epsilon of each other.
Mhm. Right, so convergent means that, right, so say A sub n converges to L. Convergent means that there exists, so given a epsilon, there exists a time such that if you pass that time, the distance of an from L is smaller than epsilon. Right? Cauchy means that given epsilon, there exists a time such that if n is bigger than n, the distance, if n and m are bigger than n, then the distance between those two guys is smaller than epsilon. Why does this one ensure that one? There's only one thing you need to say. Well,
Is that the triangle?
triangle inequality, very good. Right? Because if the points are close to L, then they're close to each other. Right? If these guys are within, if AN and AM are within epsilon of L, then they're within epsilon of, they're within 2 epsilon of each other. Right? So by the triangle inequality, you get it. So here's the proof. You're saying, well, look, we want to show that given epsilon bigger than 0, there exists an n such that if n and m exceed n, the distance from an to am is less than epsilon. Well, we know since an converges to some point L, say, that there exists a time such that if n exceeds that time, let's call this thing n prime. There exists a time n prime such that if n exceeds n prime, an minus L is less than epsilon over 2. Right? But then, if n and m are bigger than n prime, the distance from an to am is controlled by the triangle inequality, the distance from an to L plus the distance from L to an. Right? Which is smaller than 2 epsilons over 2. Smaller than 2 epsilons over 2. Right? So taking n to be n prime will do. Okay. Right, it's good. The intuition is clear, I think, right? For a convergent sequence, you can make points arbitrarily close to some point L. Right? For a Cauchy sequence, you're trying to make points close to each other. But if they're close to this point L, then they're close to each other. Right? So clearly, convergent implies Cauchiness. Okay. Yeah.
Does Cauchy imply convergent?
Does Cauchy imply convergent? So the answer
Is
is
that what we just proved?
no. We've only proven one way. Convergent implies Cauchy. So here's something to think about. So we'll get to this next time. But what about the opposite direction? What about the opposite direction? Consider 1.41, 1.414, 1.4142, etc., etc. So these guys are a sequence, the beginning, that will tend towards the square root of 2. Okay. Now, is this a Cauchy sequence? Yeah, this is a Cauchy sequence, right? Because you can make everybody past this point is within 0.1 of each other. Everybody past this point is within 0.01 of each other. Everybody past this point is within 0.001 of each other. Right? It's definitely a Cauchy sequence. It's a Cauchy sequence. Does it converge? Does it converge?
Yes.
The answer is, it depends. In R, yes. In Q, no. Okay. In Q, no. So the answer is, so the answer to your question is actually, is Cauchiness the same thing as convergence? In R, yes. So in R, Cauchy sequence, Cauchiness, is the same thing as convergence. Okay. And so there's something special about R, right? There's something special about R, which is called, that every that Cauchiness and convergence are the same thing, and that's what's called completeness. Completeness. Okay. That's generally what's called completeness. I know we called the least upper bound axiom the completeness axiom earlier, and what we'll see is that this hinges heavily on the least upper bound axiom. Okay, but generally this is what people call completeness. The fact that R has this property that any Cauchy sequence is a convergent sequence. Okay, that's it for today.